So it's about graphs, okay? So I'm going to talk about labeled graphs on n nodes with a vertex set and an edge set. And I want to count them, okay? So let's start with the easiest one, right? There are 2 to the power n choose 2 different graphs on a set of n vertices, right? That's just because there are n choose 2 vertices, there are n choose 2 pairs of vertices in the set. And any of them I can turn on or I can turn off, right? So there's 2 to that many things. And I happen to like to write it in this more complicated looking form, okay? Exponent of some constant times n squared. And I'm only interested in the leading order things in the exponent. So I'm going to say that n choose 2 is basically like n squared over 2 up to lower order terms. Okay, so that's the number of graphs. Now let's try and make it a little bit interesting by adding some more constraints. So the edge density of a graph is just the number of edges in the graph normalized by how many edges could there possibly be on the graph, which is n choose 2. And so when I normalize like this, I get a number between 0 and 1, which I call the edge density. Okay, and so now instead of, of these 2 to the n choose 2 graphs, how many of them have edge density about e, where e is whatever fixed number I want? Okay, and this is also not so hard to do. In fact, you can even write down the answer exactly, right? There are n choose 2 possible edges in the graph. I am allowed to turn on e times n choose 2 of them, right? That's how many edges I want to be present. And so the number of ways that I can choose e times n choose 2 present edges out of n choose 2 possible edges is this choose that, right? So n choose 2 choose e times n choose 2. Right? And you can approximate this using, say, Stirling's approximation, and you get, again, an answer in the form of e to the something times n squared plus lower order terms. Okay, and here the constant in front of the n squared is this function that we all know and love, the binary entropy function. Okay. So let's make it a little more exciting by putting in another constraint. So a triangle in a graph is any collection of 3 vertices, every 2 of which is connected by an edge. Okay, and the triangle density of a graph, tau of g, is defined to be the number of triangles divided by what's the largest number of possible triangles there could be, which is n choose 3, to give me a number between 0 and 1. Okay, and now I want to ask, what if I want to have a graph with a given edge density and a given triangle density? How many ways are there to satisfy those 2 constraints? So we're just getting gradually harder little by little. And actually, well, okay, sorry, that's not true. This is much harder for a reason that I honestly don't fully understand. You'll see in this talk basically how embarrassingly little we know about the number of graphs that have a given triangle density and a given edge density. But I would like to have an answer of the form that's similar to the forms that I had before, right? So I want to know, well, I would like, maybe to write my answer in a form e to the some constant, depending on my constraints, times n squared. And then I don't particularly care about the lower order terms. I'm really interested in pinning down the leading constant in the exponent. So that's the goal of this talk. Okay. Now, maybe, okay, there is a secondary goal as well, which is, let's suppose that I know how many graphs like this there are. Then the next thing that I might want to know is, what do they look like in general? Like if I were to take a typical one, what would I expect to see? Another way to say this thing is, so an equivalent formulation is, so take a random graph with a fixed number of edges, e times n choose 2 edges. Okay, I take a random graph with e times n choose 2 edges. What is the probability? The probability that such a graph satisfies a given triangle constraint, and conditioned, and what is the distribution, or what are high probability properties of the graph conditioned on having this triangle constraint? Okay, so that's the sort of probabilistic way of writing this this problem. Okay, now I'm going to go very briefly over related work just because this is a short talk, but at least I have names in the slides that you can Google later. So there's been a lot of, so the name for this problem is large deviations. There's been a lot of literature in the model of GNP. And GNP is the model where you take a random graph, and for each edge with probability P, you decide to include it or not. Right? So the point is that the number of edges, the edge density will be about P in this model. Okay, so there's a lot of work. Most of the early work was focused on the case where P is going to 0 as n goes to infinity. And there's lots of issues there. It turned out to be actually, even figuring out what the right exponent, the order of the exponent, let alone the leading constant, was not known for a while. It was finally resolved by Chatterjee. In more recent works, some of the questions that I said above have been done. In some cases, it's known what the leading exponent is. In some cases, it's known what the conditional structure looks like in some sense. Okay. In this talk, I'm going to be interested in the dense case. That is when the edge density is some constant, not going to 0. And actually, it's very interesting in this case because, like, I always sort of thought that GNP, where you weight the edges, you give each edge some probability of appearance, was basically the same thing as the one where you distribute a fixed number of edges randomly in the graph, right? Because the edge, they're concentrated and so on. But in fact, for problems like large deviations, there's a huge difference between weighting the edge probability and constraining the number of edges. If you take GNP, which is the thing that people usually study, and you condition it to have, certain triangle densities, you actually you never get a graph that has edge density E and a triangle density like a little bit less than E, for example. I may be able to say a little bit more about that in a second. Okay, so the previous work has been mainly with this GNP. We're studying a slightly different model where I want to fix the number of edges and triangles and see what happens. Okay. So before we can talk about the number of such things, we have to talk about, are there any, right? Because this is even not quite clear, right? Because if I make the edge density really big, then maybe it's also not possible simultaneously to have the triangle density be really small. So I have to figure out what are the feasible parameters before I can talk about how many graphs there are. And this was actually a hard problem in itself. It was solved in 2000. It was a classical problem in the extremal graph theory. It was solved in 2008 by Rasparov. I have drawn the picture very much not to scale, just to sort of emphasize certain features. So this is a picture where the x-axis, the horizontal axis, is the e-axis, and the vertical axis is the tau axis. And this region here is the region of parameters, e tau, for which there exist graphs with those parameters. Okay, so I've drawn in dotted line a very important curve here, which is tau equals e cubed. Okay, this clearly is a feasible, these things clearly are feasible because if I take a random graph with edge density E, then the triangle density will be about E cubed, right? Because you expect, you have a triangle, they all have to appear, so it's about, E cubed. Okay, right. Let's see, what else? So the bottom of this was actually this, so this was done by Rasparov. The lower edge of this triangle is actually made up of a countable number of algebraic curves, which you can find explicit formulas for. I maybe don't want to get too much into it. Maybe I'll just say that this point here is the point 1/2, 0. So up, when you have edge density less than 1/2, it's possible to get by with no triangles at all by taking a bipartite graph. But as soon as you get more edges than that, you have to have a certain number of triangles. Okay. So this is the set of parameters for which there is a graph with that edge density and that triangle density. And so now the rest of the game is I'm going to choose a point in here, right? A point for which the problem is feasible and ask how many graphs. Okay, so this has in some sense been answered by Chatterjee Varadhan, and then I won't say what the difference is between what they did, but also there's a result picked in Levetsky. Okay, which basically says that the answer is what I wanted it to be. Okay, it's e to the power of some constant times n squared up to lower order terms. And the constant in their result was written not explicitly, but as the solution of a certain optimization problem. Okay, so they give a variational characterization of this number that I'm after, right? And the optimization problem is I want to maximize so among symmetric functions from the unit square to the unit interval. So symmetric, I mean gxy equals gyx. Okay, among such functions, I want to maximize the integral of the binary entropy of the function, right? So remember, h is my binary entropy function. And I have two constraints. The first one is that the double integral of g should be e, my edge constraint. And the second is that this funny triple integral of g should be tau, my triangle constraint. Okay. So this is the characterization of what's the leading term in the exponent of the number of graphs with edge density e and triangle density tau. Okay. And now the whole point is that it's not great, maybe, that we don't have a more explicit form for this C. So that's what we're about in this talk. Okay, and they also showed, and I'm not in a position yet to state it precisely, that if this maximization, if it's unique, then we get to say something about what does a typical graph look like with these constraints. Okay, I want to have just a very brief aside about Graphons. The point is, I mean, as I think this audience knows very well, if you're trying to, say, study or maybe optimize over a set of objects, it would be really, really convenient if that set of objects were complete, right? So graphs are not, right? They're discrete, and so it's annoying. So what you do is you put a metric on them, you take the completion, and you work on the completion instead of on the graphs. So this is what Graphons are all about. I say very, very briefly and very, very vaguely what's going on. So a graphon is a symmetric, again, symmetric, meaning g of xy is g of yx, measurable function from the square to the interval. Okay, we put the following metric on the set of graphons. This metric is called the cut metric, and I don't really care too much maybe about the definition in this talk so much. Maybe let me point out, if instead of taking the supremum over product sets, I took the supremum over any measurable set of the square, then I would get the total variation distance. Restricting the product sets here it's a little bit like weak convergence, in the sense that, like, the topology induced by this metric is a little bit like weak convergence, in the sense that functions which have like lots of very small local fluctuations can converge to sort of something smooth, where the fluctuations are averaged out. Very vague, I know. Okay, now this is Graphons, and we were talking about graphs. Now there is a natural inclusion from graphs to Graphons, and the way it goes is I have a graph, I take my unit square, right? And I divide up each axis into n bins, one for each vertex. And then I define my function g by saying, well, on the bin, I, j, I set the function g to be 1 if the graph had an edge, and I set it to be 0 if it didn't have an edge. Right? So this makes me a symmetric function because my graphs are undirected. Okay, and yeah, it's an inclusion of graphs into Graphons. And the whole point of this is that Graphons are the completion of the inclusion of graphs in this way under the cut metric. So this way of introducing Graphons is like saying, I want to work with the completion under an appropriate topology instead of working with the original discrete objects. Okay. Yeah. There's a lot that you can say about these. I don't have time to really go into them. But let me rewrite this theorem of Chatterjee, Borell, and Dembelevetsky with this terminology of Graphons. So first of all, I define the edge density of a graphon to be the double integral. Okay, and hopefully you can see that this actually coincides with the edge density of the graph. Like if I include a graph into a graphon, and then I take its edge density, it's the same as the edge density of the original graph. And I also define the triangle density of a graphon to be this triple integral, right? And hopefully you'll see that what I said for edge density goes for triangle density too, right? If I take the triangle density of a graph and I compute that, or I include the graph as a graphon by the map I mentioned before, and then take the triangle density according to this definition, I get the same answer. Okay. So these things that I wrote is really just the generalization of edge and triangle density to graphons instead of graphs. And I also define the entropy of a graphon to be the integral of the entropy function of that function. Okay. And then this theorem that I mentioned before, you just write it in the new notation. Okay, what's the leading constant in the exponent of the number of graphs with a given edge density and triangle density. It's the supremum of the entropy of a graphon subject to edge density and triangle density constraints. Okay. And I'm also in a position to say what I meant by what does it mean for the graphs, to know what the structure of the graphs is conditioned on that event. So if the supremum is uniquely attained at some graph on G star, then most graphs with that edge and triangle constraint are close to G star in the sense of the cut metric. Okay, and this can be made, more quantitative and so on, but maybe not now. Okay. So we want to know the number of graphs with a given edge and triangle constraint. So we are interested in now solving this optimization problem over the set of graphons. And it seems to be kind of a tricky problem to solve. So let me tell you what's conjectured first. Okay. So first, a graphon is called Kpodal if it looks like, say, this. Okay. Constant on here, a different constant on here. It's got to be symmetric, so it's the same constant there and the same constant there. This is what I call a bipodal graphon, or a Kpodal graphon for k equals 2. Right? You divide the vertices into, or you divide the interval into k pieces, and then you just ask that it be sort of have this block constant structure. Okay. So the conjecture, which was based on extensive numerical simulations, is that this variational problem is always optimized for every feasible edge triangle pair, right, by a Kpodal graphon. Okay. And they actually had a much more detailed thing. So here what I've drawn in light blue is the feasible region. Again, not to scale, but hopefully you'll forgive me, right? So everything in this light blue is the feasible region, and all the lines I've drawn inside is the conjectured phase diagram of this problem. So like in each connected region here, there is a sort of analytic family of graphons, which are optimal, okay, all Kpodal, and there are phase transitions, where you transition from one optimal kind of graphon to another at these boundaries. The color coding of the boundaries has to do with whether it's a continuous or a discontinuous transition. And the number k of pods, there's countably many phases, by the way. You keep getting sort of more of them as you march up in this direction towards the top corner. And the number k of pods is supposed to increase, right? And they give names to the phases, and they have conjectures about what the structure of these optimal graphons in the various phases looks like. Okay. So this is the conjecture. And the theorem that we have, and I told you at the beginning that it would become clear in a bit just how embarrassingly little we know. So here is what we know. Okay, I have it written in text on the left, but this is, maybe I'll just draw it. So we know the conjecture in a very thin region above the curve, above this, this is the curve, by the way, tau equals e cubed, which I mentioned before, okay? We know the conjecture in a very thin region above the curve, and we know the conjecture in a very thin region below the curve, just on this sort of right half. And I'm sorry, I can't draw thin regions very well, okay? But in this green shaded region, we verify the conjecture that the optimal graphons are what, not only that they're Kpodal, but they're the specific Kpodal graph that they conjectured was optimal. Okay, and we can write things like, what's the entropy of, these things and so on. Okay. Good. So that's the main result. Let's see. I want to point out maybe one feature of it that I think is interesting, because if I don't point this out, you might not know. So the triangle density on the curve, right? So if I fix my E, the triangle density is E cubed, right? Now, in this result, I've talked about going up from triangle density E cubed to E cubed plus delta squared. In order to go from E cubed to E cubed plus delta squared, you pay delta squared in entropy. In order to increase the triangle count by delta squared, you pay delta squared in entropy. In order to decrease the triangle count by delta cubed, you also pay delta squared in entropy. So it's much easier, much more likely, if you take a random graph, to see a higher triangle density than it is to see a lower triangle density. That's what this is saying. And this actually shows through some fairly standard arguments that if you were to take a random graph here, right, and without restricting the edge density, but just weighting the edge density, you were to try to condition on having a lower triangle count, then actually what would happen, see, it's really expensive, it's really unlikely to keep the edge density the same and reduce the triangle density. It's much more likely that if you condition on seeing fewer triangles, you will just see fewer edges. So, if you do this sort of GNP thing that I mentioned at the beginning, you will just never, ever get into this position in our phase diagram. Okay. So let's see, I have a few minutes left, I think. So let's see, I want to tell you maybe, okay, here's a picture of the optimal Graphons, just so you have something to see. So this is at tau equals e cubed. The optimal Graphon on the line here is constant. Okay, if you go above the line slightly, you get this Graphon. If you go below the line slightly, you get this Graphon. And I know they look kind of the same, but there's a difference here, which is that this width is delta squared, and this width delta. So somehow, like the action, the important part of the Graphon above the line is the strip, and the important part of the Graphon below the line is the square. And they both have area delta squared. Okay, anyway. So anyway, but we show, okay, we find the Graphon, we show it's a unique optimizer. And in particular, the fact that it's a unique optimizer means that if you take a random graph with a given edge density and a given triangle density, then you know what it looks like, right? It looks, in an appropriate sense, like one of the Graphons. Okay. Maybe let me say it in a slightly more concrete way. I'll take this one, for example. If you take a graph with a given edge density and fewer triangles than you would normally expect to see, then what you get is there is a small fraction of vertices which have a much less dense connections among each other than the rest of the graph. Right? So this is the sort of graph interpretation, the graph theoretic interpretation of the picture you see. Okay, conditioned on having fewer triangles than normal, you spontaneously get this extra structure where the vertices are partitioned into two parts, and that influences the edge densities in the various parts. Okay. I want to briefly talk a little bit also about what happens. So this is, I want to lower the triangle density, let's say, by epsilon, right? Where epsilon is, it's some positive number, okay, but it's fixed as n goes to infinity. So we also talked about what happens, studied what happens if you make epsilon, instead of fixed epsilon, you make it slow, like you make it small with respect to n. Okay, and there's something interesting that seems to be happening. We don't sort of fully know. Okay, so first of all, the standard deviation of the triangle density turns out, a little computation, to be n to the minus 3/2. And there's a central limit theorem. So typical fluctuations of the triangle density are of size n to the minus 3/2. Goldschmidt, Griffiths, and Scott showed that you can go all the way up to square root of n standard deviations, and the tail behavior, like the number of graphs, it basically extrapolates the central limit theorem. Right? This is what you'd get if you said, well, I think that this is the central limit theorem, and let's just allow us to put bigger parameters in there. This is what you would get. Okay. Now, we showed that for fluctuations that are like n to the 3/4 or more standard deviations, we get a different behavior. And this behavior is what you would get if you took the large deviations behavior and extrapolated it for smaller parameters. Okay? And there's a gap, as you'll notice. Sorry, that's not this one. Right? There's a gap between these two exponents. And we don't know what happens between the gap, but it would be natural to guess that one of these two rates is the right rate. Okay, and we conjecture that our bound is sharp and that their bound is not, but to be honest, I don't have like great evidence for that. Okay, and let's see. So I had some words about the proof, which I don't think I want to show you. Just maybe let me mention that the thing about the proof is it's a perturbative proof. So we solve this variational problem by perturbing off a solution that we know, because we know that the constant graphon is optimal on that curve. So we just perturb off it and we do some arguments. Okay. I do want to show you one, if I can get it to work, a little video. Optimize for video clip. There's no sound. All right. So what we did here is we took a random graph. And if you take a random graph, then you may or may not know, but the eigenvalues of the random graph tend to follow a semicircular distribution. Okay. So this is a random graph with edge density 1/2, and I've written the triangle density up in the top left. Okay. So it's about e³ right now. And in blue, I've plotted the cumulative distribution function of the semicircle density. And in orange or red, I have the empirical distribution of the random graph. So it fits pretty well. And then I'm going to run it. I'm going to lower the triangle count. And you'll see what happens to the spectrum as I lower the triangle count. The spectrum starts to change. And then all of a sudden, the bottom eigenvalue pops out of the spectrum. Okay, it was a very sharp transition. I'll see if I can go back there. In the course of, going from 0.12205 to 0.12203, it was a dramatic change in the location of the smallest eigenvalue. And we conjecture that this is a sharp transition, actually, that there is some very interesting limiting behavior going on. But let me remind you, we don't even know the right order. So this is, something we'd really like to understand better. And I will finish with a couple open questions. No. Okay. There we go. Okay. We can only handle part of the picture, even for the perturbative result. We only know how to deal with edge density bigger than 1/2. I think the really interesting question here is the question about, like, are they all multipodal graphons for this whole picture? We have no idea how to even approach that. Okay, and also I've been talking about edge triangle counts, but of course it's also totally interesting to say, let's talk about some other subgraph, right, instead of triangles. So our methods can handle cycles, but nothing else. And so thank you for your attention.